All right, if you're in calculus, the next unit is unit 3, and it's application of derivatives. It is chapter 3 of your textbook. So I'm taking a look at section 3.1, 3.2, and 3.3 all together, because I think 3.1 and 3.2, simply put, is that if you have a position versus time graph or equation, if you want velocity, you take the first derivative. If you want acceleration, you take the second derivative. So they're really quite easy, these questions, as long as we know that. So we have a position function. We know that it's given by the equation here. S is measured in meters and time is in seconds. If we want velocity, again, velocity, first derivative. So we take that first derivative just using the power rule. So 3t squared plus 4t plus 2. Then if it's asking for acceleration, you need the second derivative. So take the power rule one more time, 6t plus 4. And we might bring this further and ask, what is the velocity when the time is 3? Or what is acceleration when the time is 4 seconds? If any of these questions, we just would need to know which equation we're looking at and then replace or plug in t. Our next one, very similar, just showing how simple these are. So you have another position time function, right? S is our position, t is time. Finding the velocity, take the first derivative. So 24.5 minus 9.1 t. I believe it's 9.1. I don't have my calculator. Oh, 9.8. Oh, yeah. 9.8 t. And then our next one, if we want to find the acceleration, then we would take the second derivative. So the derivative of a constant is just 0. Take that second derivative, you get negative 9.8. And then acceleration is meters per second squared. If we were actually figuring out some values for velocity, our unit would be meters per second, since it's in meters and seconds. The other part with section 3.1 and 3.2 would be looking at a graph. So in this graph, it is a velocity time graph. So if we were to take a look at slopes, then the slope would tell us acceleration. So when it's asking if the acceleration is positive, negative, or no acceleration, if you're moving up from left to right, like we are at point A, you would have a positive acceleration because your slope would be positive. At point B, right, if we took the slope of this line here, it would have no acceleration at that point. And at point C, going in the downward position from left to right, that would be a negative acceleration. So I think overall 3.1 and 3.2 are pretty easy. 3.3 then starts to talk about rates of change that don't have to do with a position time graph. So it might be something to do with chemistry or physics or biology or something else I can't even think of. But we just essentially, with most of these questions, when they give you information and then ask you for the rate of change, you are looking for your first derivative. So I just took some of the first few questions from the homework of 3.3. from page 133 of the textbook Calculus and Intro course. So for the first one, if you want to find the rate of change of the volume of a cube with respect to its edge length, x, when x is 4. So if you want, again, rate of change, you want to start with the formula. So we know volume of a cube is your side, which is x, to the power of 3. Now, if it's rate of change, and we know that that's your first derivative, then we would say that the derivative related to the side, d of x, equals, and then we'll take the power rule on the right-hand side, so 3x squared. Now, when it's asking exactly when x is 4, we'll take this one step further and plug in 4 for the x value, and you get 48. Our next one, same, and then in terms of units, your volume was meters, I'm sorry, not meters per second. Your volume would be, actually it doesn't give us a unit, so we'll just leave this part out. If it was a unit, we'd put the volumes unit in the top and then the volume for the edge length in the bottom. So for example, if it was meters cubed over meters, what we're seeing here tells us what our units will be. The next one, find the rate of change of area of a circle with respect to its radius when r equals 5. So if you start with the formula area of a circle, hopefully we know that that is pi r squared. And if we want to find the rate of change, we're going to take the first derivative. So the area as it relates to the radius changing. So you'll have 2 pi times r. We took 1 away from that exponent using the power rule. And now if your radius is 5, we'll plug that in. So 2 pi times 5 will give you 10 pi. And then same idea with the units. If this was, say, in centimeters, area would be centimeters squared, and then the radius is just centimeters by itself. And then this last one here looks a bit more tricky because it's a bit more complicated of a formula. But if it tells you some information about a water tank, which takes an hour to drain from the bottom of the tank, then the volume of water remaining in the tank after t amount of minutes. So this part, if it's our t value is in minutes, and it's telling us that it takes an hour, that means t has to be between 0 and 60. So it's just adding a restriction, but that even if we miss that, it wouldn't affect the problem. If we want the rate at which water is flowing, again, anytime they're saying rate with these problems, take that first derivative. So I'm taking the derivative of the volume in respect to time, and that's going to equal, so we'll bring that 2 down, we'll have 2,000 times 1 minus t over 60, take 1 away, and then this is the chain rule as well. So then we'll have to multiply by the derivative of the inside, and the derivative of the inside, right, when we're taking a look at it, 1 is just a constant, so that will go away, and then that t over 60, t would also end up being to the power of 0, so we'll have just negative 1 over 60 left on the inside. Now we are asked at what our volume would be when the tank is at 10 minutes, or what that rate will be. We're now going to plug in 10 for t. So when we do that and plug everything into our calculator, you would get 250 over 9. So the book kept it as a fraction, so we'll just keep it as a fraction. And that's the rate it is emptying, and that would be from liters per minute that we're emptying. So as always, I hope you found this helpful. Tomorrow's video, we'll take a look at rate of change when we are in respect to more than one variable. If you are also taking chemistry, please check out my channel, including my website, for videos on all topics. Thank you for watching.